This is an interesting talk. It's a talk about graph for better tokenomics. Of course, token economy is a large subject. Specifically, what makes challenging is this class of graphs, which are non-reciprocal, non-transitive, sequenced, temporal. So modeling these networks in a graph environment is interesting. By the way, one quick note. This talk is being recorded. I have already recorded it, but I am, there so that you can ask questions in the chat. I don't know how it will look like, but you can ask questions in the chat, and I'll absolutely answer. So going back, what does it mean from a token economy perspective, right? The DLT, the distributed ledger platform, is immutable, distributed, consensus-driven, and secure. Right? And it is a stack is essential for cryptocurrency and Web 3.0. Those things are in good shape, interesting things, but the security still has some rough edges. So our hypothesis is that that's what we, that graph representation and algorithms are well suited to analyze payment networks and extract fraud rings of arbitrary complexity. So the arbitrary complexity is the operational word here, because what the fraud rings and various other you know parties, what they do is they rely on the complexity, and the graphs make it easier to cut through the complexities. So our approach is, let us tackle this larger domain. Let us tackle one of the complex fraud patterns, which is basically fraud rings. And see how much success we have in that domain using the graph algorithms and TigerGraph specifically. The agenda is simple. We'll go through the concepts first. We'll have a demo. And the demo, we will see a few fantastic techniques and where to find them. I always like this movie, so I wanted to put a picture in somewhere, so I thought I got a chance to do that one. The other one is, of course, the payment networks, like we talked about earlier. There are somewhat interesting. And there are some feature requests from TigerGraph perspective that probably will be good to add. And of course, finally, lessons learned and next steps. Good. So now let us look at what does it mean to be a non-reciprocal, non-transitive, sequenced temporal network. First one is, they're not symmetric, right? Usually friends network, if A is a friend of B, B is a friend of A, right? There is a symmetricity to it, symmetric relationship. If we pay Amazon, doesn't mean Amazon is going to pay us. Second one is there is a sequence to it, right? A payment has sequence. If just for example, if you want to look at a return, a refund, right? We pay something and then we get a refund back, right? It's not like we get a refund back and we pay something, right? So there is a sequence to it. And it is not only a sequence, it is a monotonic temporal, right? Increasing time. And finally, this is an interesting juxtaposition to it. These networks are non-transitive, right? But interestingly, for fraud rings, it is a transitivity that we want to find out. But the algorithms shouldn't assume transitivity. We have to extract the transitivity out, which are not the normal, but the exception. The examples are payment networks, fake reviews, fake news. All of these things they exhibit some form of characteristics of these networks. The challenges, we did touch upon some of them. They break some of the assumptions of the traditional graph algorithms. So you can't apply traditional graph algorithms directly. And the another important aspect is in a payment network, the edges rule. So algorithmically, the nodes have a lesser role, but the payments, the time, the amount, etc., the sequence, all of these things come from the edges. And finally, so that's why we need more specific concept. This is what in the end we ask and saying, hey, TigerGraph, these are some of the things that we need to add. So going one more specific details, page rank, for example, doesn't make sense, right? If the page rank looks at it and you pay, a lot of people pay to Amazon, and suddenly if Amazon pays back something for you, say refund something, that doesn't mean that suddenly your page rank increases or you are more important. Community detection, K-clicks, these are not that relevant. So you need to be careful how you apply them. Connected component might not make sense. So these are some of the examples of why the traditional graph algorithms might not make sense, or there is a difference in the way they need to be applied in this type of networks. So let us get into it. The example, the domain is fan out, fan in fraud rings. So money laundering goes through three stages: placement, layering, and integration. Layering is the most complex. In layering, money is piped through complex web of strategic transactions, right? Mixers, tumblers, long chain of crypto transactions, cross currency. So the idea is to obscure the money trail, right? You obscure the money trail, and then of course that way we won't be able to track. So as we will see later, so let us look at it. One essential aspect is to understanding the problem is to draw graphs, right? It's graphs, so we need to draw graphs. Let us draw a happy path. What does it look like? So this is one, right? The graph one. You can see that person one, they pay to five people, they pay to another five people, they pay to another four, five people, and then it comes back. So it's this is of course two or three, one, two, three, right? Three layers. But then this could be of arbitrary layers as well as crossing ledgers, etc. Graph 2 is interesting. It is because the one of the intermediary, right, 107 also apply. They also use a structuring, layering and structuring on that end. If you look at the third one, this is more interesting because 200 is a tumbler. So their work is to layer and structure the payments and diffuse it into the network and take it out. So 201 gives you 200, 200 diffuses the payment, and then it comes back to 200, right? So these are some of the things. So as you can see, from a traditional aspect perspective, when you look at it, these are just cycles, right? You'll see later when we look at this one, these are just cycles, right? 110, 14, 1 is a cycle, or 103, whatever, right? 106, 107, etc. That's a cycle, 101, 103, 107. So that's a cycle, right? But then from a payment network, you can see that these are three distinct graphs with an actor at the helm. So you got to tease these things apart. So basically the test data set includes these graphs. The data set also includes the happy path. Right? We also should have some other normal payments so that we know that the graph algorithm is able to take them apart. Right? It knows that I should ignore these things, but that is a cycle. This is not a cycle, right? Etc. Right? So that is this thing. Challenges, so as you have heard till now, it is this particular networks. Payment network is different from social and other networks, of course. The third one, this is more very interesting in the sense that it is not just one cycle, right? People might, even though we only show like two or three graphs in there, they could do this 10 times. They could do this 100 times. They could do it, now and then 1 week from now, or now and 5 years from now. Right. So that is where the temporal comes in, the arbitrary complexity comes in, as well as multiple cycles come in. Lastly, of course, the technique for ordering is a needle in the haystack, right? There is a high class imbalance, probably 3%, 5% or something as the maybe more, but it's not. It is not 50 or 60%, right? So the thing is, it is you have to go through a lot of transactions. You have to go through a lot of edges. On the other hand, it's also interesting because once you go through that one, the cycles are smaller. So you don't have to go through the larger data set. Again, once you identify the cycles, you have a smaller data set where you can do more complex algorithms. So the approach, taking a cue from what we were talking about, layered approach, right, progressively narrow down and then work on them. add sequencing as much as possible. One of the good things about TigerGraph is that they have the graph algorithms and you can customize them. So that's good because you can customize the algorithms and that will come out very nicely. Add runtime attributes to it. So you will see I have added a few runtime attributes. We should be thinking of adding more runtime attributes that we can extract from the graph. The symbol schema, start from a symbol schema and then add elements as required. And the last one is very important. Stay in TigerGraph as much as possible. As you will see later, we stay in the TigerGraph. So that means you have to have a lot more object conversions and lists and all kind of stuff like that. You have to keep them and then you got to go through them again. But then remember, we are going through them progressively. So that means even though you go through billions of nodes and transactions in the beginning, as you narrow them down, you don't have to go through all of them. So let us go to the demo. The questions to ask, are there cycles? That's the first question. Second is, can we resolve them to fraud rings, right? Can we unroll the transitive sequence temporal operations into fraud rings? Third is, can we find out who is at the helm of a fraud ring, right? That means the sequencing temporal, understand it very well to do that one, capabilities in the platform. How many cycles? So remember, this is one of the things that you can add as a part of a dynamic attribute. And finally, what is a full path? Can we see a graphical view? So let us, without further ado, let us look at that. So I have the TigerGraph, the Graph Studio. So one thing, I have saved this particular solution as exported here. So you could in the because they want to make sure that they can reproduce it, reproducibility, transparency, openness, right? So because of all these things is there, you can import that one. So if you import that one, you will get it directly, and then go to the Tumblr network. Tumblr network, the design. The schema is a very simple schema. For now, I'm only using these to the account and the send. As we will talk more, we do need to make it more complex. We do need to add more things. One of the interesting things that you see on the right side is a time tree. We do need to have a time tree, but I'm not using the time tree yet. The mapping comes out simpler because we only have one or two the edges and the accounts. All of them nicely go in there. Loading data, that works out fine. The test data, probably, I don't know, 100 and some rows. So 100 and 200 edges, etc. So, and 74 wedges. So it's just a simple graph so that you can track them, test them, make sure that they work, etc. So the query, let us look at the query. The query that is the ordered payment cycle, right? That's a query. So the first thing, like we talked about earlier, find the cycle, right? So if you go in here, you will see a cycle list. So the cycle list, I find the cycle list using the RT cycle algorithm, which is available in the, right? You can, this is the algorithm that is available in TigerGraph. And the good thing about TigerGraph is that you are able to customize it. So I customized it as well as added a few defaults, etc., so that it makes it easier, right? So let us go back to our ordered payment cycle and let us run it first, right? Once we run it, then we can look at and inspect the various things in there. So it's running. Takes a little time. Of course, we got the running. So the thing is, this looks very strange, but if you look at the tree view, you can see that nicely you got the three graphs. Remember the three graphs. We'll look at it more closely. So let us first see the cycle. Right? So let us look at what it has, the output. So if you look at it, you see that it has the cycles. It has all the cycles in there, 176, 107, 106, 101. So the thing is, it doesn't know this view. right? It doesn't know this view. So it just mixes up everything, right? It looks at it and says 110, 14, that's a cycle. I know 101, 105 is not, these two are not cycles, right? 101, 107, 106 is a cycle. So it says, okay, that's a cycle, but it doesn't know that these are multiple graphs. Right? That is where we have to do more things in there to take it apart. So a cycle comes in, and then what? So when we go in here, then it goes through a set of a set of object transformations. One of the things that I do is use heap accumulator. So once you have an heap accumulator, you are able to sort it. So this is where we can unroll the temporals. But of course, you can't put an edge in there, so you have to create an object for the heap accumulator. So once you start the heap accumulator, you can put a heap accumulator. Once you have the heap accumulator, you can go to the top. When you go to the heap accumulator top, you can nicely get the people at the hub. So that's what happens here. So let us look at it here. If you look at it here, when we go down, that top ID, right, the top of the heap, top of each heap, right? Actually, probably it has 3 heaps in there. That's why, right? It has got 3 heaps, which are our 3 products, right? See the 201, 101, 1, right? If you go in here, this 1, 201, and 101, it's able to take them apart. It's able to take them apart. And of course, remember this one here, remember we are talking about the dynamic cycles. Yes, you can do a dynamic cycle. It tells you. So this thing, it actually puts back as a part of the node, right? 201, for example, is part of 5 cycles. So that way, later, we can, when we want to do other things, that particular property or that particular field is available as a part of the node. Going back, let us see whether all our questions are answered. Are there cycles? Yes, it's able to find the cycles. Can we resolve the product? Yes, we can, right? And who are at the end of the product? We can find that out. How many cycles are participants part of? We can do that one. Graphical view of the full network. By the way, it also has a JSON view of the full network. So we are able to look at all of these things. Let us look at the network, right? This is good, right? So this is the first network. It does it very well. It finds the money laundering network nicely. It correctly identifies the fraud actors at the helm, right? It nicely identifies the fraud actors at the helm. If you go to the next one, this is easier, right? Much easier. The frauding is evident. This becomes a little harder because when you look at the visualization, it, it, it this visualization, right? It becomes a little because it's difficult to route. But I just connected it and routed it in spite of the subviews, right? Because of all the Tumblr, etc. It still works. So challenges, right? Some of the feature requests. The first one, what happens is even though because we have the edges, so we only we have the nodes, so we have the nodes that are all part of the fraud. So you only need the edges that are part of those things, but it's difficult to get that one directly. This whole object hierarchy is slightly difficult to handle because you can't have a set within a list. The edges are not first-class objects. I would have preferred a heap accumulator as an edge, because if you have a heap accumulator as an edge, and if you're able to put, then you can take that edge out and do other things, right? You can go in and say, start from these edges and do other things out of that one, right? If you take an edge apart and make it into a tuple, then it loses the property of an edge. Then you'll have to go back and search for the edges and all kinds of search for the objects and nodes and all kinds of stuff like that. Another thing is the fine-grained temporals. We do need a time series to unroll. Probably it will be good to have a object composition and graph algorithms with some internal default optional property of something to do with. I know that these things are not that easy because we also have to think about the parallelism, etc. They are not in one node. So you have to, how do you sync up with all the nodes, and how do you partition it? All of those questions are there. I do agree that, but still these will be good things to have. Feature engineering for graph neural networks, that will be interesting because now that we have all these dynamic attributes that we can generate, right? Graph-based dynamic attributes by applying these algorithms. Now we can actually use them for graph neural networks. Lessons learned. So first of all, graph representations are appropriate. It works fine. It works fine. So the first thing is the most important thing is spend time thinking about it and understanding the problem, right? You have to understand the problem very well to put it into a graph algorithm, right? Like anything else, but this thing is more interesting and you got to do the thinking. And of course, to help it make simplified assumptions and relax them as you progress. Think graphs and more specifically parallel graphs. This is where I had a little interesting time. But of course, by the time I started thinking in parallel graphs, things start to come out, come come nicely together. It takes a little time. Actually look at the graph algorithms, the GSQL code, read, write, learn. As you can see, I have written a few things and then tried all kind of things. And in the beginning, maybe the object structure might be a little clumsy. And then as you understand it, you'll realize, oh, I don't need this one, or I can use a set accumulator. I can use an accumulator. I can use this one in accum, etc. Create data sets. Important, create data sets with multiple scenarios, try them out. And the last one, like I talked about earlier, do as much as in TigerGraph and staying true to the platform. It is tempting just to say, okay, give me the cycles and let me go out and give me all the properties. You can do that one, right? You can get all the properties, but what you should do is stay there because that's where you will see all these graph algorithms and object conversions and all kind of things like that. Because I wanted to stay, and I will stay more. It's not over yet, right? I got to. One of the things that I need to look at is because of the heap has become a tuple. I got to now roll back into objects and etc. Right? Working on it as we speak. Try things to try. One is scale. Bitcoin, Ethereum, cross ledger will be interesting to try because once you have cross ledger, there'll be more complexities that will come in, but it'll be interesting to try that one. The second one, of course, like we talked about earlier, fine grained temporal. You do need to add the time tree and things associated with that one. Otherwise, and also remember multiple cycles. How do you disconcern between multiple cycles, uh, which are maybe years apart or months apart or maybe minutes apart. Derived dynamic runtime attributes. I have to apply other things. Like even though, like we talked about earlier, community and in degrees, out degrees, all of these things, right? Even page rank might work to some extent. Graph motif extraction and weighted graphs. So there is another interesting vector to try out. Graph neural networks, like we talked about earlier. And finally, entity resolution. Because even though the R accounts are not the same, because you have this whole spans, right? What happens is if you have a huge span, if you have a exchange, etc., right? You have huge number of addresses going out and in, right? So you have to understand those things and you have to figure out. Otherwise, you'll have to, if you start tracking for cycles for everybody who is coming into an exchange, there'll be a lot of processing. So I don't know how to handle that one, but my thought is that if you have entity resolution, if you know what these things and have a slightly more complex, uh, uh, expressive schema, then that will make it easier to do the things. Maybe eigenvalue, centrality, graph neural networks, all kind of interesting things that we can try. So in short, a lot of things to try. A good start. Uh, and that's all. Thank you very much for taking your time. I'm here actually to answer your questions. So ask questions now or later. Discussions are welcome and interesting to see what your experiences are, etc. So thanks a lot.